Okay, so today we're going to talk a little bit about potential difference and currents through an electrical device. So I have an electrical device here, and I already know that if I want a current I to flow through it, I have to have a potential difference across the device. Basically, one end of the device should be connected to the higher potential plate of a battery, and one end of the device should be connected to the lower potential plate or the negative plate of the battery. So if I have a battery, in this case a cell here of potential difference V, that provides a potential difference V. So this potential difference, if I make a connection like this potential difference is appearing directly across the device, and this potential difference is responsible for pushing this current I through the device. Okay, so where does the potential difference comes from? It comes here from the battery. Now, of course, to make this current flow through the device, the battery is doing some work, and we discussed last time that this work done by the battery is the total charge that the battery pushes through the device into the potential difference of the battery. And since I is Q by T, I can replace here Q with I into T, and I can get another expression for work done by a battery, which is V into I into T, where V is the potential difference of the battery, I is the current that the battery is pushing through the device, and T is the time for which this current is flowing in the circuit. Okay, now there are two type of devices. The question then arises, first, is there some kind of a relationship between the voltage that appears across the device, which is here the cause, and the current that flows through the device, which is here an effect of this cause? In ohmic devices, yes, there is a very linear relationship, which is V is directly proportional to I. Example of an ohmic device is a bulb. To review what is direct proportion means that if one quantity increases by some factor k, the second quantity also increases by the same factor k. So in other words, in a bulb, if you double the voltage, the current doubles. If you triple the voltage or the triple the potential difference that is appearing across the bulb, then the current that is flowing through the bulb will also triple. But not all devices follow this direct proportion between voltage and current. There are certain non-ohmic devices where there is no such direct proportion between the voltage and the current. Example is an LED and a capacitor. Okay, moving on. If V and I are in direct proportion, which is known as Ohm's law, remember that if two quantities are in direct proportion, their ratio is always a constant number. V by I is always constant. Here, this constant is known as R. R is what? R is resistance. Resistance is the property of a device, and it is also dependent on temperature. It is a property of device and temperature. So V by I is R. This equation is more commonly written as V is equal to IR. Remember, V here is the voltage that appears across the device, I is the current that is being pushed through a device, and R is the resistance of the device at some certain temperature. So different devices have different resistance values. Just to tell you, give you an example, a 1 watt bulb has a very high resistance, and your 100 watt bulb has a low resistance. Uh, Now moving on, resistance also changes with temperature. In semiconductor devices, as temperature increases, the resistance decreases, while in conductors, uh, as temperature increases, the resistance increases. Okay, so we won't go too much into that. Okay, suppose some certain constant temperature, that is my assumption that the temperature is not changing. I have a bulb here, I have a voltage source here, and this voltage source is causing a potential difference V to appear across the device, and again there is some current that is flowing through the device. Suppose I have some way of changing this voltage or changing the voltage that appears across the device. Now if V and I are to be in direct proportion, as V changes, I should also change, and they should change by the same factor. So I have written here some hypothetical values to just show you the effect. I have a certain set of voltages here. For a voltage of 20 volt across the device, the current through the device is 0.5 ampere. Now here I have doubled the voltage. The value of the current has doubled. I have tripled the voltage. The value of the current has tripled. I have made the voltage 4 times from the original set, and the value of the current has also gone up by a factor of 4. For all these values, the ratio V by I is 40 volt per ampere. See that 20 divided by 0.5 is 40, 40 by 1 is 40, 60 by 1.5 is 40, and 80 by 2 is also 40. So 40 volt per ampere. This 40 volt per ampere value is the property of a device, and it is also the property of a temperature. Okay. So this here will be known as the resistance of the device at this certain temperature, which is 40 volt per ampere, and this volt per ampere is written as by this symbol, squiggly looking symbol, and the symbol is known as ohm. So I will say that the device here has a resistance of 40 ohm. So similarly, all ohmic devices have a certain resistance, which is simply the ratio of V upon I, which ratio is a constant. So to summarize, if someone say that you have a device of a resistance of 1 ohm, it will mean that the ratio of voltage and current will be 1. In other words, if you apply 1 volt potential difference appears across the device, then a current of 1 ampere flows through it. Okay, so that's it.